So today we start our next topic. So we have studied single species dynamics last week, logistic growth, and generalized questions about single species. And last two classes we studied competition between two species. And our next step now is to study two species which are in a relation called predator-prey dynamics. Okay, you have a predator and you have a prey. So, and the way to do this is very similar to competition. We will have to have two functions, one for the prey and one for the predator. They will be functions of time, and we will have two differential equations, one for each of the variables. And then we have to model how predation affects the population dynamics of prey and how predation dynamics affects the population dynamics of the predator. But now, first we have to make some assumptions because they will be important. So we will start with a simple case, which is the following. So we want, okay, so competition is typically what represents the bottom-up regulation of a population, okay? So predation represents top-down regulation of the population of prey. So I will assume, to simplify and to isolate the effects of predation on the effects that affect the prey, I will assume that there's only top-down regulation for the prey. Okay? So this means that if there is no predator in the system, the prey can grow exponentially. Okay? So if I put the predator in the system, then this exponential growth will not happen anymore, but it is not due to a carrying capacity. It's due to the presence of the predator. Okay, so this is the simplifying assumption, the initial simplifying assumption. Okay? So in the next steps, we will relax this assumption, and then we will see how this will modify the results with a simple model, and then we will then go on and have models that are more complicated. And so we have two classes for predator-prey dynamics today and tomorrow. So next assumption. I will assume that the predator is a specialist. Predator preys only that prey that I will be putting in the system. So there's no other alternative prey. Okay? So it's a very simple situation. Okay? And what does this mean? If the predator predates only the prey that is being described, so only one prey, in the absence of the prey, the predator cannot increase the population. The predator can only decrease the population, so only die, okay? Because it has no influx of prey. Okay? So these are the simplifying assumptions for the first steps that we will get. So we will have two functions, and I will use P of t for predator, and I will use V of t for the prey. Why V? Well, I use the notation of the book of Gotelli, and where V is victim. Right? So it's easier to remember in this way. Okay? So, and we will have to write two equations, one for V and one for P. And so let us start with the simplifying assumptions. I'm supposing that the population of V can grow exponentially if there's no prey, no predator. Therefore, let me just, it's just the best. I will assume this. And then I have to put something here, which will be the effect of the predator. And I will also, just let's see for notation, okay. Assume that in the absence of prey, this guy will have only a negative, linear negative decrease rate. So something like, I will write it here, some constant times p. So this is just with a negative sign means that this would be the balance between birth and death rates in the absence of the prey, saying that there's only death rate, there's no birth rate, because the only way to have a birth of predators will come from the consumption of prey. So now here I have to write something which has to come with a minus sign, which is the effect of the predator on the prey. So the first thing is I will assume that this is proportional to the number of prey. So if I have, say, one prey, I have a certain number of prey being consumed by unit time. If I have 10 prey, then I will have 10 times this consumption. This is a hypothesis that can be relaxed. In this case, we are not considering that predators in great number could interfere between them, among them. So I'm not considering interference between predators. So if I have one predator, two predators, or three predators, then the number of prey of consumers is just proportional to the number of predators. But can it be only here? This term obviously cannot be true, because this would say that even if I don't have any prey, say V is 0, then I would have predation on 0. That cannot be true. So there must be something here, which I will call a function f, which can be a function in principle of p and v. And okay. And then I will suppose, so this has a name, and this is things that you will hear a lot. It's a functional response. And then I will suppose that the number of predators that arises from the predation of the prey is just proportional to this one, but with a constant in front. So that would be P times F of PV times a constant, usually it's chi, so Greek letter, which is a kind of efficiency. So the idea is that this predation will somehow, we have to write down F, because for the time being we have only considered that there will be a function. Now we will see which function we want to put there. So, and this is called numerical response. It is a common assumption that the numerical response is just proportional to the functional response, and at the end of the day, we only discuss the functional response because the numerical response is proportional to it. But you could imagine I have other models also. So, is this okay for timing? So, because now I want to discuss the functional response. So a big part of the discussions, of theoretical discussions concerning the predator-prey dynamics is discussing the functional response. Right? So there are usually in the classical text, there are three functional responses that are important. Right? These are called Holling's person that developed a lot of functional Holling type 1, 2, 3, 1, 2, 3. Okay, so we will discuss today Holling type 1 functional response, which is the simplest case, and which is the case that has been originally discussed by Lotka and Volterra. Okay? So I will assume that the functional response is such that it does not depend on P. So this corresponds to no interference condition. And the Holling type 1, okay, type 1, is the assumption that f of p v does not depend on p, and it's just proportional with a proportionality constant to v. Right? Okay, but some step back. So what is the functional response? Let's think a little bit of it. Okay. So this gives me, okay, this is the growth of the prey. Forget it about now. Here is the number of prey, variation of the number of prey in time. Okay. Suppose you have one predator, and this here is what? It is the number of prey consumed in time by one predator. And or you could also say that's the number of prey consumed by unit time per predator. Okay? Okay, so this is something more mechanistic now. Like yesterday we were all with the stories about the phenomenological model, but this is in principle something that could be, you could run experiments and see how many prey are consumed by one predator, by a typical predator. Okay? So, and what I am assuming when I say that I will suppose that the Holling type 1 functional response is that this predator, the number of prey consumed per unit per predator is proportional to the number of prey. This means that if I have 10 prey, okay, then the prey will be consumed at a certain rate by the predators. Okay? And if I have say hundreds, I mean, let's better say, if a predator can consume, say, in the presence of 10 prey, if the predator can consume, say, 1 per unit time, in the presence of 100, then it can consume 10 times more. Okay? That's it. Okay? I give you a sandwich, you consume it. I give you 2 sandwiches, you consume it also. I give you 10 sandwiches, you also be able to consume. And obviously, this is something that we will discuss probably tomorrow. That's an assumption that the predator has no satiation. Okay? There's no satiation, and there's no need to manipulate the prey, because you could could be a physiological limitation to consume more prey, like I'm satiated, I cannot eat 1,000 sandwiches. But also, similarly, what can limit the ability of the predator to consume prey is the fact that maybe it has to manipulate the prey. And this takes time. And then I cannot go on consuming more than a certain number of prey per unit time. Okay? So I'm supposing for the moment here, that the prey is not satiated, has no satiation, and obviously this could be true for if the number of prey is small, and then this is a good approximation, for instance. Okay? So, okay, keep in mind that this can be modified by assuming something else about the predator, about the ability of the predator to prey. So let us write now this equation here in the form that I have here. So this is called the Lotka-Volterra system. And it dates back to the 1928, 27, something like that. Okay? So, okay, so we have a system of equations which describes this simplified situation about predation, which is that we have a specialist predator, exponentially growing prey, no satiation being taken into account. Okay. Well, okay, now what's the common thing that people would do in this? After the class yesterday, you probably already have an idea. So first, again, the same story. We cannot write down the explicit solution analytically. Again, we cannot do this in terms of known functions. No way. Well, then what we can do is numerical analysis, and this is part of probably what Renato will be talking in the, I don't know when exactly. What was the next topic from Renato? He already is in differential equation. Okay, so you know. So I will be a little bit of repetition today because I used Renato's quote. Okay, so he advanced quickly. So, okay. And besides numerical stuff, what can you do is do the qualitative dynamics of the system. Right? Again, looking for fixed points, looking how the behavior, the general behavior of the system is. Okay? So, having paid attention to what we have done in the last two classes, you would say, find the fixed points. Okay? Then it's curious, because, okay, we can do it. It's very easy to find the fixed points, because I have only to have the fixed points will be R V minus alpha P V is equal to 0, and key alpha P V minus mu pi P is equal to 0. These are the conditions for the fixed points. Okay? And So we have the fixed points, and we will suppose that P and V are not 0, okay? Because if P is 0, we already know there is no fixed point. There is exponential growth of V. And we already know that if V is equal to 0, that's exponential decrease for P, so no interesting situation. So we have to suppose that P and V are not 0, and then you can cancel this here, which implies that P that if you cancel P, that V is equal to mu over alpha T. Okay? Easy. Only one fixed point. Now, so then you would go to the diagram. Let me just see. That's the best way to draw this diagram here. That's V here and P here. Okay? And then there's fixed point here where V is equal to mu over alpha T, and V and P is R over alpha. Easy. Okay? Now, okay, we have the fixed point and we want to know if it's stable or not. Okay? So, in the last class, we resorted to a graphical analysis. Okay? We can try to do it here. Okay? But we'll see the problem. So, you have to write down the null lines. Okay? For the first equation, what are the, would be, you can cancel the V. The first equation, the null line is just R minus alpha P equal to 0, which is a constant value of P. So the null line is just this. And for the equation below, it's just Q alpha V minus mu equal to 0, and therefore it's just this line. So there's straight lines in this case. Again, straight lines, but at a 90-degree angle. Okay. So then you would start to look again for the arrows, and now it's not anymore that here everything grows. Okay, because if, for instance, if for V, okay, if V is smaller than this this value here, okay, let me see. Correct? No, it's not correct. So I'm taking this from the book, and I just discovered the book is wrong. Curious. The number of victims, okay, so this was curious. So the book is wrong. That's fabulous. Okay, we discovered that incredible. So I'll have to do the calculation. So, okay. So let's start with P. Okay, if P is very small in this region here, this thing here tends to be positive. Okay. Okay. And if this is positive, means that this is, okay, yes. If that's not so easy. If P is positive, if P is small, okay, the book was right. If P is small here, which is this region here, small, then this term tends to be positive because R will dominate, and this term appears for the dynamics of V. Therefore, V will increase here and will decrease on the other side. Okay? Which means if P is bigger than R over alpha, then this term here will give you a number that's bigger than R. Therefore, this is a negative number, and the dynamics of V will be decreasing. And now the same story for the dynamics of for dynamics of V. If V is small, okay, then this term will be negative. Okay. And this term is negative, appears in the equation for the predators. Therefore, this will be a negative value. Therefore, it's down. So let me just put this here better than this way. Okay? And when V is bigger than this value, then this term is positive. And this appears in the predator, which means the predator is increasing. Or this is proposed this way. So let's see if the book was right. Yes. So the resulting tendencies will be this way, this way, this way, this way. Right? So what does it mean? If I start here, I go in this direction. When I come here, I will go in this direction. And when I cross the line, I will go in this direction. And when I cross this line, I will go down here, and I will be back to the beginning to this region. So it's kind of something which looks like circular, right? But you could have thought, now this could be going on like this. I start here, I go here, and come back here. But I could also go this way and not close the trajectory. I could just have a spiral. Two possibilities. And the fact is that the visual analysis cannot distinguish both cases. Okay. Therefore, you need algebra and analysis. Okay? So, what happens is that, so small explanation of how do you do this analysis. I don't want to do it because it needs linear algebra and so on, but for people that have mathematical training, it's very easy. You just say, I consider I'm at this point here, and I consider small perturbation. And then I look through the Lotka-Volterra equations, what is the solution? Is this small perturbation going back to the point, or is it going away? And this is not difficult to do with using linear differential equations, exponential functions, and so on. But the curious result is that for Lotka-Volterra, if you perturb the fixed point for a small amount, it will not neither approach the fixed point, neither go away. It will stay close, but no tendency to go back, no tendency to escape, which is called neutral stability. It's neither stable nor unstable. It's called neutral stability. Yeah? And in these cases, you have oscillations on the oscillations. So the actual trajectories, so these are called trajectories in the phase space, or in more mathematical language, they are called orbits. You have V, you have P, you have the fixed point, and near the fixed point, you have something which is like this. Okay? Now, this is one thing, but now, depending on the initial condition, you will have other orbits. Right? And the other orbits will be like this. So, for each of the orbits, okay, for each initial condition, you have one trajectory here, and it's a closed trajectory. Okay? So, let me show a little bit better the trajectories. For instance, this is a numerically worked out example. So these are trajectories, and the P prey and victim prey. In this case, the same not the predator is called N, but never mind. Yeah. So these are closed trajectories. Now we have to discuss what these trajectories mean. Okay? So now we want, so I didn't show you the solution for the time being. We didn't show any solution. We are just saying I have a system, and I have a fixed point, and I have trajectories that all of them, the fixed point is here, but you have trajectories that go around in orbits that are closed. Notice that are very close to the fixed point. It's actually very close to being a circle, but not when you go for larger orbits are not circles. Okay? They are deformed, like they are closed, but they are deformed. Okay? And that comes from the fact that P and V cannot be zero. Otherwise, you would have only circles. You have at a certain point you'd go and cross this one, okay? Cross the axis, which is not okay. So, very well. So, now, let me see. I think I have a nice figure here. Okay, where are the figures? Figures. This figure is nice. So let us discuss this figure here. Oh, okay, a question. Here's, probably this is the bad mic, but let's see.
I think you're going to actually answer my question now, but I will ask anyway. In the case of the orbits, do we have a tendency of larger orbits going to the stable point in the center, or opposite, or it just stays in the
They
same orbit?
stay there.
It stays.
Stays there. And at the end of this class, you will see that this is a problem.
Oh.
Okay.
And what determines in what orbit the predator-prey relation
The initial
is?
condition.
Initial conditions.
Yeah.
Okay.
So because you have, I mean, these are some of the orbits, okay? But there's an orbit passing at every point. So if I start here, there's an orbit here, and it will stay on this orbit, okay? And if I start here, there's an orbit here, and it will stay here. It's not that you have, say, 10 or 20 orbits. You have an infinite number of orbits. At every point, there's an orbit going on, and I'm just singling out some of them in order to have an idea.
I know you're just talking about top-down regulation, but does that mean that if we have a disturbance in the ecosystem, such as bottom-up regulation, for instance, can the relationship shift orbit because of a disturbance?
Yes.
Okay.
We have no disturbance here, but you can shift orbits. Yeah. And that will also come exactly in the final part of discussion. First we show how beautiful Volterra is, and then we show it's useless, and that will have to do with this, but we will probably tomorrow, be able to have a much better model, which is a generalization of this, which will not have all the problems that we will discuss about Volterra right now. So first, okay. Here you can see, let's say you start at a point which I wrote down here as 1, okay? You have a certain number of predators, a certain number of prey. Okay. Well, over time, you will be on the orbit. Okay? So you will go on. And here, you go on, and the number of prey is increasing. Okay? Increasing, and then it starts, P starts to increase here. Okay? Now P is increasing, V is increasing. But at a certain point, P increases, but V starts to decrease, goes back. And then it goes back, a long time back. Okay? P is increasing, V is decreasing, but at a certain point, there's a reversion, and this, well, it's not well, it should be a little bit more like this. Here, P starts to decrease, and V, at a certain point here, will start again to increase, slowly and then quickly, and then come back to this point. So what happened? I started here and came back here. This means that the motion goes back to where, the trajectory goes back where it started, which means that you have a periodic solution. Okay? After a certain amount of time, there's a certain period after which you get back to where you started. So that's called a periodic. And here we see that this periodic solution has to do with what? With oscillations. You start here, so let's say P first. Let's only look for P. P increases, decreases, increases, decreases. And the same thing for V. Okay? V increase, decrease, increase, and so on. So they are going up and down. Now, these are oscillations. Notice, we have no external perturbation whatsoever. So, these oscillations are intrinsic to the relation predator-prey. Okay? They are intrinsic. Okay? Well, okay, now, I said, okay, well, but come on, show me the solutions. So I will show you the solutions. But you already had them with Renata, but I will make it this. Maybe you didn't understand Renata's class, you have a second chance. So I just took Okay, so there's a graphical depiction here, oscillations, okay, blah, blah, blah. What about the solution? So the solution have this is graphical, more with some fantasy. The solutions look like this one, okay? So you have the hare, which is the prey, and you have the lynx, which is the predator, and this is a famous system of, I will talk to you about the history of the system, but before, you see, the blue line is the hare, okay? So it starts increasing, gets to a peak, and the lynx starts increasing later. So only when it already has a certain number of prey, then it will start to increase. So first this one, then this one, and then the hare decreases, and this continues to increase, but then it will also decrease, and so on, and so on, and so on. Okay, so it's an oscillation. And what does it mean? Is it reasonable? Well, that there should be some oscillation is reasonable because we are doing something which was the simplification of a specialist predator. And so the number of prey starts to increase at a certain point because there are only a few predators. It increases, okay? Because look at the equation. If there are very few predators, this one will dominate. It will be positive. Okay? So the number of prey increases. And after the number of prey increases, the number of predators will increase because there's a lot of prey. But then it decreases to a point where it depletes the population of prey, and this population of prey will start to decrease. And after decreasing a lot, what will happen is that the number of prey will be a small number, and therefore the number of predators also will decrease. And then it starts again. Decreasing the number of predators will make the number of prey increase, and then all the story again. So that there should be some oscillation with the simplified assumptions seems something interesting. Okay? So now the exact form of these equations depends on the parameters. Okay, this is an example taken from a book, and I don't know the parameters actually, but you can go and use, this is taken from Renato. I don't know if he used the same here, may improve this. So you write a Python code for the Lotka-Volterra equation. Here you define your equation, okay? I think that maybe, I don't go into the details, okay? But you see the R is our R, the C is our alpha, E times C, E is our chi, and D is our mu, okay? So, and so that's exactly the Lotka-Volterra equation. You have to give some initial conditions, and you give some values for parameters. For instance, this one, if you run it, you get this here. If you change the parameters, then let's say, what will be the effect, for instance, of increasing the efficiency, the chi? It's like this. And the efficiency is that you have the functional response, is the number of prey consumed by unit predator over time, over by unit time. Then consuming a certain number of prey will generate the birth of a certain number of predators, but it's not that you consume 10, that you will have 10 predators. There is this factor which is the efficiency. Okay? So if you increase the efficiency in this equation, then probably you will have bigger populations of predators. Okay, so let's see if this is true. Here, this plot is with an efficiency 0.3, but let's say we put it to 0.9. Okay, so then we run it. Okay, and you see, if the efficiency is large, then you have oscillations almost of the same size, but with a shift. It is the predator that the prey that starts to increase, and only after some time the predator will increase also. Okay? So it starts to increase, so on and so on. So, and then that's it. And then you can write down, for instance, that here these are you can make the phase plot also. So, and here you have 3 phase plots for 3 different initial values, or 4 initial values. Okay, there's a small problem here. And these are the plot, the things that we have seen here and in the previous figure also. Okay, so now what we want is to consider if this can have some, if this is reasonable, plausible. Right? So the first thing is, well, are there situations where you have oscillations between predator-prey dynamics in nature that you could? So this is not an easy question. Why? Because system predators and preys are not isolated in the world. Okay? So there are other species around that will be perturbing, and maybe the perturbation just makes the oscillations disappear. Okay? And moreover, that is a particular result that for the time being, this result is valid for a specialist predator with no satiation and with a prey that increases exponentially. So that we will see that how this will change when we relax some of this assumptions. For the time being, that's it. So it could be like, okay, is there such a situation? Maybe it's difficult to see. Well, usually in very cold regions in the Arctic, then you have things that resemble this. And there's the classic example of the hare and lynx oscillations in the northern regions of Canada. So first you'd say, okay, how do you know the populations of lynx and hares in the northern part of Canada over, I don't know, over tens, I don't know, I can't remember, it was like 30 or 40 years. Right? It's a time series, a long time series. Okay, I should have. I didn't bring a picture of it. Okay, let me see if there's a picture somewhere. I don't think I have a picture. Okay. Let me see. No, I forgot to bring a picture of this data. It's in the book of Murray, Jim Murray's book. Okay, and. Is it maybe here? No. Oh. Ah, yeah. Well, it's so small that you won't see anything. But actually, these are plots over from 1845 to 1935. So even more time. Okay. And you have here the number of hare and number of lynx. Now, how do you know this? So this is. It's not the number of hare, not the number of lynx, it's a proxy. And the proxy is that these things were hunted, these animals were hunted. Okay? And you had the Hudson Bay company, which was centralizing, buying all the hunted animals for commerce, and because they are food for fur and this kind of thing, and then you see oscillations, and the number of what you look is on the accounts of the books of the Hudson Bay Company. Okay, so okay, it's not the best observational setup that you could ever imagine. Okay, because you are just saying that maybe there was a financial crisis and they didn't buy the thing. Okay, but apparently not. But then you see these oscillations. Okay. Now the point is with this thing is, okay, this is a kind of example, and nice example. There's another example which is non-numerical, and it's just the story how Voltaire got interested in this situation. So Voltaire, which I thought is a very important mathematician, he was spending his some summer vacations in a city which is Ancona in Italy, and he met a guy that worked, very smart guy, who was called Umberto d'Ancona, and this guy worked with fish stocks, okay? So with fisheries, and he told Voltaire that there was something very curious, that a certain species of fish had the stocks oscillating, but it's not every year. Because every year, let's say that it's just seasons. No, it was oscillating every 3.5 years, kind of very weird period. Well, where does the period of this kind come from? And then going on and talking more, he also mentioned that it's not only these fishes that they actually wanted to fish, but also the small sharks oscillated in the same period. So this led Voltaire to consider that maybe there's a relation between these sharks, because they are predators, and the fish that were being of interest for the fisheries. And so he proposed this system of equations that has oscillations, and therefore he proposed that what was behind these oscillations was a predator-prey system. Okay? So, smart, nice, and this has nothing to do with Lotka. Lotka worked independently of this. Okay? And actually, Lotka studied much later predator-prey dynamics. It should be the Voltaire equations only. But well, everything which comes with Lotka and Voltaire, they kind of connected forever. Actually, they didn't even know themselves. So there are these oscillations. Now, are they the oscillations described by the Lotka-Voltaire model? Okay, so oscillations exist. So there's also the general question beyond this topic, that if you see oscillating populations, or in a more ecological way of saying this, if you see cycles of populations that are cycling, what's the region of the cycles? So one of the things is maybe it's seasons, but I mean, seasons is 1 year. So you'd expect then, if it's a seasonal forcing, that it is 1 year, or maybe it's a multiples, 2 years, 3 years, 4 years, sometimes due to some complicated thing that the cycle. But you expect an integer number of years as the periods. Okay. Well. So if you don't see this, then there's probably the oscillations are coming from something else. Okay, so one of the possibilities that these oscillations are connected to predator-prey dynamics. So the importance of this work is not that it is precise experimentally, because we will see now, and we will start to see what are the problems with this work. But the glory of this work is that it discovered that there can exist cycles in nature that are intrinsic to the relations between the species and not due to something environmental. Okay? That's the big discovery of Lotka-Volterra model. There can be cycles, and these cycles come only from the population dynamics and not from something external. Okay? That's the importance. Okay? Now, okay. Is this okay for the time? For the time being, it's like only the beautiful things. Now we will start with the ugly things. Okay. Now, cycles like this have periods. Okay? So the time it takes to get back to the initial point. Okay? So you could ask yourself, what's the period of the oscillations? Okay? So it turns out, this is not easy to see here. I forgot to mention something about the links and hairs, which is curious. If you look at the time series of links of hairs from Hudson Bay Company, there is a period where the links starts to increase before the hair, as if the hair was hunting the links and not the links hunting the hair. So that's a problem, and you see that obviously this means that there's something fishy going on with your method of observations, which is just going and looking for how many animals were hunted in the books of the Hudson Bay Company. So that means that this data is an illustration of oscillations, and it's one of the first examples of oscillations, but actually there are problems that probably this is connected to hunting activity being more focused on one species or other, which depends on the market value of the animals and so on. To see, then it was not a really observation that is independent of the dynamics of the hunters, which are men, humans. So, okay, let's get back to the discussion about the period. So there is a period. Now, it is not easy to calculate this period, and actually you cannot find a form to calculate it. But it's not so difficult, and maybe we can do this with this program here. Let me go back here. Let me go back to this one. So, if I look at this thing here, okay? So there is a certain period that I could look here, okay? So it is about what? Like here is like 6, and here is like 14. So more or less 8 units of time, for instance, okay? More or less. So, okay, then I say let us start with a different initial condition. We are starting with 1, 3. Let us start with 10, 30. So I have not even run for sufficient amount of time in order to see the periods. Let us here, instead of 50, put let us put 100. Hope it runs quickly. Okay, so you see a completely different period. Okay, and if you go on changing this thing, instead of 10, 1 and 3, you put 5 and 10. Run it. You get something here. Well, and this is more or less than 30, and this is more than 40, so it's over 10. It's bigger than 10. So you see the period depends on the initial conditions. And this means what? Any point here, this trajectory has a period, and this other trajectory has a different period. And this trajectory should have a different period. Now, that's not so okay. If you go and you look for links in aerodynamics in the northern part of Canada, it is, you find, and there are separations due to geographical obstructions. There are subpopulations, and they all have the same period. They are synchronized, actually. Okay, so they have the same period, but they don't have the same population sizes. And this is not explained by this. Here, every initial condition creates an orbit which has a certain period, and the periods are not the same. So there is no intrinsic oscillation for the system. And this is not in agreement with what you see, at least for some of the populations where you have a good reason to believe that they are connected to predator-prey dynamics. Okay, so this is a problem. Okay? So you expect that a good theory will have a preferred orbit, a preferred period that is intrinsic to this system, and not something that you have a period and then you have, depending on the initial conditions, you have a different period. And going back to your question, if you have a perturbation, you add a period, and then you have a new period, and you don't go back to the previous period. Oh. So what you expect in a more realistic situation is that, yes, maybe we can have cycles, but there should be a preferred cycle with a certain period. Okay? So instead of having something like this, you'd expect to have a good certain cycle which is more important, which is the cycle that it has a certain period, and if you start outside, you approach the cycle. And if you start inside, you also approach the cycle. That's what you would expect from a more reasonable situation, that you perturb your system, and it goes back to the orbit, which is not anymore, we don't call this actually, it's not a fixed point, but it's a kind of attractor, but that's technically called a limit cycle, right? Which is a cycle in the phase space that is attained after you have gone through some transients. Okay? Now, I want you to give me an everyday example of a cycle of this kind, of a cycle that has a preferred period, and if it perturbed, goes back to the period. Ideas? So cycles, oscillations.
Tides.
Hmm?
Tides. Ocean tides.
Yeah, ocean tides, well, they are not so much perturbed. It's an interesting thing. It's completely out of the subject. But there's a certain number of waves that arise per unit time usually, and this is constant over the world. And why? It's not very clear. Okay. So, there was somebody raising the hand? No. Okay. Oscillations in every day, which can be perturbed. Hmm? Photoperiod. Yeah, but I mean, photoperiod is it's not perturbed. Okay, it's fixed. Okay. I mean, it's completely deterministic. So it's not perturbed actually. Okay, in everyday life.
In the circadian cycle, our
Inner clock. Yeah. I mean, you could perturb your, but this inner clock is your, yeah. More or less, I don't know exactly. Hmm? Hmm? So, temperature. Well, temperature is not actually, well, there's an oscillation in temperature due to the day and night. And it actually does, it's not the preferred oscillation. I mean, the period will be the same, although it will not be actually periodic, because some days are hotter or it would be. It's always a one-day cycle. Okay, the main. I mean, there are many cycles. A one-day cycle and then a seasonal cycle also. But these are fixed by astronomical effects and not perturbed. Where's the? Okay, you. Okay, where's the mic? Mic. Go, mic this way. Hmm? Hmm?
Fire in the Cerrado.
So, fire in the Cerrado is well, there's a mixture of human-made and then there's natural dynamics of fire in the Cerrado, and obviously the human part is it's not so controllable, but if you look just for the natural fire in the Cerrado then this is usually determined by the seasons, and this has a fixed period. So there's a perturbation. It's not actually, there are years you have more fire than in others. So it's not exactly periodic, but it's oscillating anyhow. But the oscillation comes from astronomical things, which are astronomical things are not perturbed.
I don't know if it is exactly related to. I don't know if it is exactly related to periods, but I guess our heartbeat rate, it can be disturbed by some exercise, and then we go back to a basal level.
Yeah, that's the answer I wanted. Our heart. I mean, I have a certain rate here, say 80 beats per minute. Okay, then I run. I get 120. And I stop, go back to the previous situation. But if my heart were a Lotka-Volterra model, I would stay with the 120 forever. Okay. So only a new perturbation would see. So the heart is what there are mechanical models for hearts, heartbeats, and so on. And actually, they have limit cycles in the sense that there is a preferred period. The period depends on the person, on the physiology of the person, obviously. But then there's a period that is the preferred period, which is the natural period. Okay. Okay. So you wanted.
Well,
I was thinking about gap dynamics in a forest. When a tree dies and leaves some space open, and then there is something that happens there, the
So succession.
succession.
Succession. Ah, but I don't see cycles in succession. Usually, you have some extreme event, like a tree that clears a part of the forest, and then you have succession, and you have the first some species which dominate the situation, and then the others, and so on. But it's not really a cycle. Okay? It's not a period in this case, because the fact that it's generating this dynamics is random, which is the tree falling. Okay, that's why my computer went to sleep.
I thought of something similar to Kelmer, which like stress levels, but I also thought of like traffic. You can have an accident and then traffic accumulates and then it goes down again.
Yeah, but the difficult point is what would be traffic is not naturally oscillating usually. It depends on the configuration, okay? But if you have just a big avenue, it will just go and like a laminar thing, and that would be not oscillating, okay? There's a perturbation which creates oscillations, true. But these oscillations will die out in order to go back to the natural thing, okay? So it's a fixed point. It's not a limit cycle. Insist.
Maybe the plankton migration,
Yeah.
you know, the plankton migration from deep water, from surface water, and then deep water, then surface water. It happens every day.
This one I don't know, actually. I don't know. I can't answer this. It's very particular, and so I don't know. Maybe. Right? So okay, so there are limit cycles in nature, and you expect the cycles that you see in nature to be limit cycles and not this kind of thing, okay? But, well, so there's another problem, actually, which is called in mathematics. I don't want to give a formal definition, but this system here, it would be non-observable. Why? So everything in nature is under perturbations. Okay? So you start here. You start here, and you are going here. And then perturbation. Rain, whatever happens, that perturbs the population. So maybe you jump to this point here. By a perturbation. And then you go on like this. And then another perturbation takes you there. And then another takes you more over here. And then you go still here, 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 and then you go back here. And then maybe you stay on the curve, and then you get here, and then stay on the curve, then you get back here, and then you get to this one, and you go on a little bit on it. Then you got here, then you got here. So you'll never get back to the initial point, actually. There's no reason, because there's so much perturbations. So this would only be observable systems that are described by this kind of cycles, which are not limit cycles, in very special conditions when you either don't have perturbation or the perturbations are really, really negligible. Okay, so this is something which is called in modernity. This system shows structural, does not have structural stability. Okay, so it is typical of things that So for the physicists, it's also interesting, and physicists like conservation laws, and actually this system has a conservation law. And that's what makes it have this kind of cycle. So it's like, if you look at Hamiltonian dynamics, it's more or less the same. Okay? So these are cycles that cannot describe a field experiment and so on. So that's the problem with Lotka-Volterra model. Okay, then you would say, okay, how can we like the cycles actually, but they are not the good ones, let's say. Okay? No.
Tell us some examples.
What?
Those cycles with species.
Well, I just told a lot of them, but for instance, the lynx and hares in the Arctic region. There are also dynamics of voles in Finland and northern part. Then there are dynamics of fishes, which have between fishes and predator and prey fishes, like sharks and other fishes, that oscillate in time. So these are cycles. They go up and down, up and down. Now what I'm saying that these cycles that you observe in nature, these equations imply that predator-prey dynamics can induce cycles. Okay? So the examples I just gave are examples where they are not connected to cycles of the seasons or a day or a period of 1 day or a period of 1 year. They are not connected to this. They have periods that are like 3.5 or some random number. So then you could expect that this cycling that you see is connected to predator-prey dynamics. Okay? And then there are examples where it is actually connected to predator-prey dynamics, and you can also produce a lot of this in the lab with microorganisms. So there is the fact that we have cycles in nature that are connected to the intrinsic nature of predator-prey dynamics is something that is true for many systems. Okay? Now, it's true for many systems. What I'm saying is that we discover the cycles with the simple assumptions here, but these cycles that we found should not be this. This phase diagram here has problems in describing what we see in nature because it has this periods are different depending on initial conditions, and this is not what we observe. You do this kind of experiments with microorganisms, and you can do this, and you can do it with different population sizes, and you still will see the same periods, not different periods depending on the population size. So that's the thing. So we have to put some more assumptions. So you have to modify the assumptions that were used to build this model to describe oscillations that are actually seen in nature. Okay? So we have. I don't have time to work out the examples. But, tomorrow we'll modify this equation. But as a last discussion, so what are things that we could modify? What hypothesis could be modified such that that will change this equation? So ideas. So okay, now with the mic. Well, mic. Is here.
Maybe we could introduce a handling time for the predator or satiation, which are similar.
Yeah, they are similar actually. Yeah, and okay, this is a good idea. That the only how should this? So handling time stuff. But how will we do this? That's more complicated. Okay, so one thing is that this term here is connected to the consumption of the prey by the predator, and this predator is able to get, if you give him more prey, it will consume more prey. Maybe that's a maximum number of prey. And so maybe this proportional to V here should not be, and so here's the functional response, but forget the P, so this is just linear function of V, okay? So this is the consumption, and in here the V, and this is just something like this. But maybe there should be a maximum of prey that a predator can consume per unit time. So maybe it's just something that goes to an asymptotic value. So could be an idea, which would be to modify this term in order to include satiation and handling time. So there was another, you raised your hand? No. Yeah. Okay.
Thiago said that we could change the functional response.
Yes, functional.
But what if we change the exponential growth of the population of prey without the predator?
Okay, so sure that in nature things do not grow exponentially. So one idea is to put a carrying capacity for the prey. Okay, just notice that then you have the prey is not anymore regulated only top down. It will be regulated top down and bottom up, because it's a bottom up phenomenon, carrying capacity. But sure, including carrying capacity should at least say something like, when I go to very large values, large cycles here, they should not be allowed, because maybe they just represent a too big population of prey, which cannot be sustained by the environment. We didn't talk about the environment, but the environment here is very rich, sustains exponential growth. If the environment contains limiting resources, then somehow this thing should not go as to too large values.
But it will not reach a central limit like we are trying to do here. It just large values of prey is not possible.
Yeah, then something has to happen here. Yeah. And
yes.
We will see that the next step actually in analysis is to do this. Okay.
I think what was going to say is something similar. I was going to say that include the dynamics of like a plant that the rabbit eats too. So there's a third variable there.
Yeah. Okay. So one thing is model the consumption of the to a tree trophic model. Okay. There's the resource of the prey. Okay. So the prey can also prey upon consume something. There would be another thing. Yeah, sure. But well, we will do this in the next class in the other way. It's just putting carrying capacity. But if we have time, we will also discuss trophic chain with tree species, for instance. Okay. So, any other idea? Modification. So there are many modifications that you could do. So we want to still stay with things that are pretty much general. Okay? So we want to look at systems where you have some reason to think that they are regulated top-down, and don't go into particular systems. So, for instance, satiation is always there. There's no such thing as an infinitely voracious predator. Okay, so this will be general to modify this. And carrying capacities for prey is also general. There's no such thing as infinite carrying capacity. So these things can be introduced in the model, and still you have a general discussion. Well, then sure, then you have papers which list hundreds of functional responses, but they are particular to to a certain system. You can actually, there are studies of functional, experimental studies of functional responses. Okay, and if you have organisms that you can manipulate a little and so on, then you can maybe have functional responses. Okay, you have a predator, and you see how the consumption of the prey depends on the number of prey, the rate of consumption. So this is in principle something which is, these are, well, obviously this is not very, it's not a super long experiment, but you need some time. What is much more difficult to observe is the numerical response. Your numerical response needs, it's not directly observable. You have the consumption of prey, and then you have a certain birth rate. And this will be modified by the consumption. Then you have to have a certain time scale, and you probably would have to run a very long time experiment. So I'm not aware of any direct measurement of the functional response. So the typical thing is just assume it's proportional to the functional response. But functional responses exist in tens, hundreds, lots of things, but they are particular to certain systems, okay? And we will see, for instance, one other phenomenon that we have not included is that this functional response is like P times V, and we had written, if it's still here, is it? Yeah. We had written this in this way, which could in principle depend on P. So dependence on P can be interference between predators, or could also have a positive, more predators are able to be more efficient in predating because there's a group effect. So this in principle could be modeled by the functional response. Okay, either negative, since the high number of predators, maybe they start to fight, but or maybe a certain preferred number of predators that is more efficient than a small number, for instance. That could be group behavior, group hunting, for instance, okay, which exists. So this is another thing. This one we won't discuss, but you see, there's a lot of space to new models that can be much more specific to a given situation by playing around with this guy thing. Okay. So I think that's all for today. So what's the script for tomorrow? Tomorrow we will start by introducing a carrying capacity and see what happens, and then we will be very sad with what happens, actually. And then we will introduce a handling time for the predator, and then we will be happy again. And at the end, we will discuss the problems of the thing. But we will come at the end to what's called more or less the standard model of predator-prey dynamics. Okay. So, okay, that's all. Thank you.